is continue on with a little bit more on rectangular coordinates, some normal tangential coordinates, and near the end we'll get to the introduction to using polar coordinates, which you'll find actually quite interesting and useful. So what we'll do today is we're going to start out with a problem out of the book that relates to some homework problems you've had. So I have it projected up here on the screen. It's number 64. And I can lay something underneath here to make that a little more level. So this particular question, what we have going on here is we have a frame where a pin is inside that frame, and the frame is moving upward at a constant 3 feet per second, or 3 inches per second. So the frame here is moving upward 3 inches per second. And at the same time, then that pin is sliding in this parabolic groove. Sliding in this parabolic groove. And the question asks, calculate the velocity and the acceleration of the pin when x happens to be 6 inches. In other words, when the pin is 6 inches from the y-axis shown there, over to the right. You folks want to try that first, or do you want me to just go ahead and go through the motions with you? What would you prefer? You want me to do it? Since I'm not seeing any heads nodding up and down? Okay.
Why not?
Okay. So, I think everything here is in inches and time is in seconds, so we can just stay in that realm then. So we're not worried about having to juggle units to make the units consistent. So, I'm going to go over to the board here, and we'll go ahead and draw that. The function is x equals y squared over 6. And that function is a square root type of function, quadratic, opening to the right, like this. And I think they were asking for the velocity and the acceleration when the pin is, when x is what?
6.
When x is 6. So at x equals 6 inches, we're looking for the velocity and the acceleration. Do they show vector symbols there or scalar? Is it boldface type in the book?
Scalar.
Scalar values. Okay, we want the velocity and we want the acceleration when x equals 6. What we do know is that any location here, they told us that the vertical component of velocity, because of the frame motion, is constant at 3 inches per second. At 3 inches per second. So the Vy is equal to 3 inches per second, and that's a constant. And that's Vy right there. Now the key to doing a problem like this is reading carefully that wording, and that means no matter where the pin happens to be as this guide moves upward, that vertical component of velocity remains that value. So at the position I have it shown here, we know that the true velocity is pointing which way?
Along the path.
Along the path, always along the path. And so we know the true velocity is along the path, in other words, tangent to the path right there. And then if this vertical component of velocity is constant, then that means there is then going to be a horizontal component that has to be perpendicular to the vertical component. And so the true velocity happens to be that value, that length, scaled length, on the tangency at that instant. When the particle is up here, again, we have this 3, we have this Vy term being constant, and we know again the velocity has to remain tangent to the path. So you can see clearly, given that rough sketch, that the velocity is going to increase as that arc sweeps over and becomes more and more horizontal. That's something to really watch out for. You'll see mechanisms like this later in the course and probably in other courses where you have a driver, something like this arm that is constantly rising at a constant rate, or possibly in a manufacturing process it might be rising at a constant rate for a moment and then it might stop, might go back down, might come back up, that kind of a thing. So then you can actually design the response that you would want to have for a pin and maybe something then hooked onto that pin. So let's see, we've got a little math to do. We're looking for this information right here. So I think we need to do some stuff over here with this. What would you suggest we do with this quadratic function in y?
That's a position function on the x-axis. If we integrate that one, we can get a velocity function for the x-axis.
Integrate this?
Differentiate.
Differentiate? Yeah, okay, differentiate this with respect to?
X.
Okay, if we want to differentiate with respect to x, we will find then, well, let's go ahead and do it. Differentiating the function with respect to x. So x equals y squared over 6. Differentiating with respect to x, we're going to get 1. And actually, I'm going to go just do this so that we can sort of track what's going on. 1 equals, and then differentiating over here, you have to use your chain rule. So we have 2y over 6 times dy dx. And so dy dx turns out to be equal to 3 over y. Okay. So we can think about that for a moment. What does dy dx represent on that graph? What does dy dx represent?
It's the tangent.
It's the what?
Tangent.
Well, it's the slope of the tangency, isn't it?
Yeah.
This is the slope of the tangency on that curve.
I got a question.
Question?
Why are you treating y as a function of x?
No, that's just because that's what was suggested.
Yeah, it's just a
Okay. Now that could be useful information potentially. Okay. Now let's see, who asked that comment, made that comment? Okay.
Why are you treating y as a function of x was the question.
Why?
Yeah.
Well, you mean the differentiation with respect to x?
Yeah.
Well, just because that was what someone suggested. Now I'm just seeing where the math takes us. We are able to get a little insight here. Do you understand what this is then? Okay, and that's okay with everybody? All right? Okay. So this is the slope of the tangency. Now, could we get at the velocity and acceleration from this piece of information?
Not really. We don't have time.
We don't have any time specified here, do we? We don't have any time specified in this. So why don't we come back and take this quadratic function, quadratic in y, and differentiate it implicitly with respect to time. Okay? So what we want to do then is take that same problem and this time differentiate it with respect to time on the function on this. So we end up with dx dt is equal to, and again, you have to implicitly differentiate this. So first of all, we'll differentiate with respect to y squared over 6, and then we will differentiate y with respect to t by the chain rule. So we have dx dt is equal to then y over 3 times dy dx, or dy dt.
We know that dy dt is 3.
And dy dt is equal to 3, so this is equal to 3 inches per second, constant vertical rate of change. So if we put that in there, then dx dt is equal to y over, just the value of y, And what would be the units on that?
Should be inches per second.
Inches per second. So dx dt is, in other words, dx dt, if this is v, and dy dt here is a constant 3, then this is going to be the dx dt reading off of that. Okay? Now, can we answer the original question? What's the speed?
Not yet.
Okay, what do we need to do to get the speed? We're trying to get this value of v. We know this is constant. We have this expression now in terms of a value y, and it turns out to be in inches per second.
Okay. Can't you just add?
But what is y?
We can solve for it.
Up here, this implies, doesn't it, that y is equal to the square root of 6x? Y is equal to the square root of 6x. So using that piece of information, let me label that 1. And so if I substitute 1 in to this equation, then dx dt is going to be equal to the square root of 6x. This is going to still be in inches per second. And the problem asked, what is this speed? What is the velocity when x happens to be 6? So at x equals 6 inches, dx dt becomes square root of 36, or 6 inches per second.
Oh, okay, that's just a component of, right?
That's a component of the velocity then, shown here on this drawing. So then on this sketch, we have 6. We have a ratio here at this instant. This is 3. This is 6. And here is the speed at that instant as this thing is on that, as this pin is on that quadratic path. So this v right here then is going to be the square root of 3 squared plus 6 squared, 36 and 9, 45, which we want to simplify to 3 radical 5. And that's going to be in inches per second. Is that all right?
Different route, but same answer.
Okay, good. What route did you take, Ian?
I integrated dy dt equals 3 inches per second, and then found
Just
y.
a second. Let me write that down.
Sure.
You said what?
I integrated the differential dy dt equals 3 inches per second. The initial
Okay.
velocity of
So another
constant
approach
velocity of y.
is that dy dt is equal to a constant 3, integrated that over time, and got dy integrated over time.
Note that based on the diagram, the initial position of the pin is 0, so that t equals 0, y
to
equals
some y. So you got y equals 3t.
Mm-hmm.
Okay.
I substituted that back into the x equals equation.
Okay, but x was equal to y squared over 6, so you ended up getting 9t squared over 6, which reduces to 3t squared over 2.
So that this, now I have both the position components of the position vector, the x and y, so I took the derivative of both of those.
Okay, so this one right here gave you dx dt is equal to 3t, and
That one, of course, was already
this
3.
one was constant,
So then I just plugged in t equals, well, actually, I had to solve for the time.
And then he had to solve for the time by choosing a value x equals 6 and got y equals 6.
Right.
Is that right?
So
X
I-
equals 6,
yeah, I
y
just-
equals 6.
Mm-hmm.
And then, with that in there, you were able to find the value of time,
Which turned out to be 2.
2, and then we're able to determine the two components of it there. Okay, good. So now a different approach on it. How about, let's look at, we didn't finish the question, did we? One thing you want to be very careful about in engineering problems is when you get done, you go, oh, man, feeling good, on to the next question. Go back always and reread the darn question, because oftentimes there's more there, and this is a real simple illustration. We were looking for also the acceleration, magnitude of the acceleration at this point. Now, here is the path, isn't it? This is the path. And this thing is doing what? Speeding up or slowing down
Speeding up.
as it moves up there. Does everybody agree that it's speeding up based on what we talked about here earlier? You can see it visually right here. Little short velocity. And as this thing becomes vertical, actually when this becomes vertical right here with the pin at the bottom on this parabolic path, right here it's vertical, isn't it? It's motion. How fast is it going there?
The same as the bar frame.
3 inches per
It
second.
matches, doesn't it? This given arm that is rising at a constant speed of 3 inches per second. So right at this instant, the speed on the arc is exactly the vertical frame speed. And then this thing speeds up. You can see it graphically here, speeding up to there as it moves across that arc, that concave down arc. So what's happening to the tangential acceleration? The tangential acceleration.
Yeah, it's becoming greater.
Is it 0? Is it positive? Is it negative? It's positive, isn't it? Do you have a sense of that? It's speeding up as it moves up along this arc, even though the vertical part of the speed remains constant. So it's kind of like you in your car hitting the accelerator. So it's speeding up. Now, we've learned at least enough, we're developing a sense of we're on a curved path here, so there's a tangential component of acceleration that is positive along the arc, and there's also got to be another component because this is a curved path. We saw yesterday in the last session that there has to be another component pointing which way? Towards the center of curvature. Towards the center of curvature. So there has to be then, and we have a tangential component of acceleration. We also have a normal component of acceleration. If this thing's going to be on a curved path in motion, it's got to have something that's causing it to come that way, arc over this direction. So it's got to have that. So the total acceleration then is somewhere down in here. You with me? Anybody? Okay. This is something that sometimes slips by people to even, you can get through a dynamics class and pass it and everything, but you don't really get this real sense. But I'm trying to point out these spots of trouble so that you'll be real clear on them and you won't have that confusion. Everybody feel good? Okay, we're speeding up along the curve. The curve is arcing off to the right like this, concave down. And so there has to be a component of acceleration everywhere on this path that is pointing towards that center. Okay, how are we going to get the acceleration? From the tangent and normal components. The thing is, we only know that the vertical velocity component is constant. So what I might suggest is we came up with a first derivative relationship here, which relates the x component of speed and the y component of speed, right? So I think we could hit this again, couldn't we? Couldn't we differentiate this again and see where it takes us? See where it takes us? So why don't we do that? I'm going to switch over now on this expression. I'm going to write this as x dot using Newtonian notation. And why don't I move the 3 up here on this side and let that be equal to y dot. Okay? Now let's come on in and differentiate this differential equation. So we have 3x dot equals y dot. Every one of these variable functions here are functions of time. So if we differentiate, and I'm not sure where this is taking us. I'm just playing with the math to see if we can get some insight. So 3x double dot equals, over here we have a product of 2 time-dependent functions. So if I differentiate the first and leave the second one alone, plus our product rule, the opposite combination, leave the first function alone, differentiate the second function, we get this. Second order differential equation. Now, can we simplify anything here? Think about what we know in this problem.
Yeah. Y dot is equal to 3.
Okay, y dot right here is 3. Oh, so that becomes
9.
I like that. Okay. This becomes 3 squared. Here we have 3x double dot plus y double dot. Acceleration in the y direction. Why is it 0?
Because it's constant.
Oh, see, y dot was equal to 3 inches per second constant. And so y double dot is then equal to 0. So this term zeroes out on us. I like that. Feeling good. So look at what this is. I wasn't sure where this was going, but we end up with x double dot is a constant value of 3 inches per second squared. X double dot is 3 inches per second squared.
What did we lose an inch on top of that? No,
Oh, you're looking at the unit analysis
looking at the
in
units.
there? What happens is this term is, you have to watch out where this 3 came from. See, it was carrying some units with it when it comes over in our previous calculation. And we end up with, see, this is going to be like inches squared per second squared here, inches squared per second squared. And then this thing is actually looks like it's carrying inch units associated with it. And so that's going to give us inches per second squared in the result there. Yeah.
Couldn't we just differentiate the dx dt equals y and gotten the same thing?